All right, David, are you ready?
Yes, I am.
Hey, David's getting ready here. Peter, are you ready?
Good.
Everybody got their coffee? Remember, no such thing as a stupid question. We love your questions, And this is about people talking to each other. Are there any questions that were top of mind as you came back from break that you want to ask, or anything on Zoom? Anything that was like sitting on your head that you just want to talk about? How does one go about collecting such data as we're going to share? So Y charts is a syndicated data feed that you basically pay them. It's not inexpensive. They basically take publicly reported data from every public company. And because of accounting rules, there are certain things that people have to report. And they report on different quarters. They may restate, and they'll report on different currencies. So what Y charts does is it synchronizes the different reporting schedules, synchronizes the shifts in currency, and also helps us with any restatements so we can be sure that we have the most current data and account for mergers and acquisitions. So we buy the data. We classify the data based upon the work we've done on industries, because SIC codes and NAICS codes are not good monikers for dividing the industries. And then we work on data cleansing on the back end. If we've got a hole in the data, then we go back to Y charts and we collect it. But we've been working on this data set. A lady by the name of Regina is online, who we got to give thanks to. Regina has been working on this data set for a decade. And so one of the issues we had when we were working with George Runger is we did not have as big of a data set and as clean of a data set to work on. And so one of the things when we started working with Dr. Goldsman was, we had worked on this data set for quite a while and it was pretty clean, right? Yeah, so good question. Other questions, anything top of mind as you come back from break?
This is Shri on Zoom. I had a question on the Gartner 25 report that you showed. I believe you said the peer group was exceeding the leaders in performance. I was just curious to know how Gartner or the leaders listed in your report reacted to your analysis. Have they made any changes to how they measure or do things internally based on your research?
So the question is, did Gartner respond and change their methodology? No, I've done this for 6 years now, where I've compared the supply chain stood Meyer to the Gartner Top 25. It really bothers me to see the reference to the Gartner Top 25 in the industry literature and academia. The other thing is, the Gartner Top 25 is really set based upon people's input. So it's 50% opinion. It's the analyst input. It's supply chain leaders input. So what is happening is we are really driving a false belief about supply chain excellence based upon, this commonly held view that companies like Procter & Gamble or Colgate are the best in the industry. I mean, Procter & Gamble and Colgate do some individual things very well, but Colgate has never beat the industry in inventory, and Procter & Gamble has never beat the industry for the last decade in growth. And so, what we hopefully can get is an evolving methodology, but I'm trying to get education around, it isn't the individual metrics, it is, are we driving value, and how do we have a balanced scorecard that can align the organization across the functions and across the people to be able to drive a balanced scorecard, and how can we get that in the technology so that it can be actionable and we're just not measuring costs. Does that help?
That helps. Thank you very much.
Yeah. Other questions? Okay, David, it's your show now.
Very good that you explained Y charts a little bit. I'll more say about that too. So I can talk for hours, as my students know. That being said, feel free to interrupt, ask any questions. I'll do my best to try to answer them. This can almost be sort of an open-ended discussion. I'll show a bunch of charts and go through a lot of analysis, but I'm also willing to skip over that if people start yawning. It turns out we now have some hot mics here, And if you have a question, we can actually have somebody come over and give you one of them. Like, maybe Elijah will help me with that. Yeah. And if you don't have any questions, we can do karaoke with the mics. And so, okay. So I'll talk about some of the statistical analysis that we did. I'd like to acknowledge Joseph, he'll be back in a little while. So I'm on my own if there are any questions with regard to the programming. I work with Benoit Montroy, who is one of the head honchos in Supply Chain Logistics Institute here. Unfortunately, he's not here today. He's been very important. Gamza Tokol is in the back. You can say hi. She's a statistician, faculty on campus as well. She's been extremely helpful throughout the process. I saw that Matt Spooner was on the line online, and he's been tremendously helpful. Typically, the cycle that we would undertake is we would have supply chain experts, say Laura, Regina, Matt, and others, give us information that we could use to input to our models. We'd run the model, they'd see something they didn't like, maybe change it a little bit, but it was all because of them that we selected proper inputs and decided on, for instance, market cap per employee as the output. So really happy to see Matt here. Okay, so again, if anybody wants to interrupt, totally no problem. I'll go over a little bit of what Laura had already talked about. I'm going to give a few more details. So this Y chart is actually very, very interesting. Again, it's a subscription-based data provision service. And we were working in a data-rich environment, lots and lots of data, many, many companies, many different sectors, lots of fields per company, and lots of years. So this is 40-ish years worth of data. And I have to say it was pretty well cleaned. This is owing to Regina. She did a great job. It turns out there were a minimum of 114 input fields, independent factors, maybe not really so independent. We'll talk about that. These are the performance metrics that were used to estimate various dependent measures that we were interested in. For instance, market cap per employee. And even though these are sort of independent factors, and I've seen people just throw them into a model, a lot of machine learning models, for instance, you would just toss them right in and they would use them. We're a little bit more careful about these types of things. And it turns out that a lot of the independent factors were not independent at all. They're sort of the same measure, maybe with a tiny little change. And of course, they're highly correlated with each other. We'll show you some charts in a little while. 114 is an awful lot. We didn't want to put all those into a model. At the same time, we have Laura and Matt asking us to keep the models really simple and actionable. So there was no way we're going to get away with 114 inputs. There's no way we're going to get away with 10 inputs. And so after all the fisticuffs that I talked about, we settled on smaller numbers, and actually pretty reasonable, turns out. So it turns out there are 26 different industry sectors. We ended up looking at 13 of them in pretty good detail over a 40-year time period, and we're currently attempting to use last year to do validation of our results. Okay, so to begin with, I'll walk you through what we did sort of at the beginning, and then after a little while, we'll get to sort of the more current models. So we selected a particular industry, actually 3 of them, considered 30 years of data as a starting point. It was interesting because we had so many independent, allegedly independent factors, and we were tasked with building smallish models. What we decided to do is we took these more than 100 factors and we clumped them up into, let's call them independent clusters. And there are methodologies to do that, various different ways to do the so-called cluster analysis. So what we did is that we would take these, say, 114 inputs and group them into 5 clusters that were more or less independent of each other. So you can sort of see that makes sense. Even though the 114 variables might not be independent, you could at least get them into approximately independent clusters. And that would allow us to do sort of standard regression analysis on representative inputs from each of the 5 more or less independent clusters. Does that kind of make sense? And again, that also helped us with keeping the model sort of simple. So then we perform regression analysis on at most 10, but usually about 5 factors to model this market cap per employee. We did very simple, really simple elementary regression first, no transformations, no funny stuff, just to see how we would do. And then we would do more advanced techniques later on. Our first goal was just to see how we compared to George Runger's models from before we knew we were going to do fine. And then after having picked 1 or 2 or 3 sectors, we would rinse and repeat for, it turned out to be 13 sectors. And eventually, I'll get to that. You'll see how it did. So here are the different sectors we eventually looked at. You see, the first 3 are the ones we attacked first, and then we looked at these other guys, finished them off about a month ago. Actually, it was very interesting. It turns out, you might have noticed this from when you were taking classes, once you would spend a month working on a model. Laura's a little less patient than we are, and doesn't want us to spend 1 month per sector, because that would be 1 times 13 equals over a year, right? Laura's time frame is a little quicker than ours. But it turns out, once you do 1 model, the delivery time gets chopped. Joseph was able to crank these things out very quickly. We got good at it. We delivered these submodels pretty quickly. And you can see these are the numbers of companies in each one of these sectors. And I guess maybe I didn't know this. I guess these are all public companies, right? Yeah. For some reason, I didn't know that. Okay. Oh, and by the way, I should mention that the way that these companies are divided up, if you're at a consulting company, this is not necessarily the way that you divide the companies up. But this is coming from Supply Chain Sid Meier. Is that? Yeah. But if you can do the analysis for one of these sectors, you can make your own sector up. So it's not like this is really difficult. Okay, so here in the initial phase of our study, which we presented a few months ago at an Informs conference, these are, I'm just saying, giving these as examples of sort of typical variables that went into the models. Again, because we were trying to be kind of simple-minded, this is in totality, the list of variables that were included in some model that we were looking at with respect to these initial 3 sectors. And you can see, just looking at this, that days of inventory is going to be highly negatively correlated with inventory turnover. We would not include both of those quantities in a particular model because of the high correlations. But of those 12 input variables, each of those was included in some model. And most of the models would tend to have 3, 4, 5, 6, 7 inputs by the time we were done with it. Since Gams is sitting in the back, she was always reminding us, whether or not Laura tells us to keep the model small, if you don't absolutely need independent variable in a model, if it doesn't add anything, get rid of it. That's called principle of parsimony, where you should be, you get penalized in some ways, depending on how complicated you make the model needlessly. So anyway, then it turns out, I think somebody must have asked a question about this earlier. There's almost always a time component in models. Now sometimes if you don't need it, and I'll give examples where that might happen, you can get rid of it. But it turns out the time component never really hurts to have that in there. Now, where might be cases where you don't need a time component? Well, it could be if you're looking at a relatively short, very stable time horizon in your model. I'm thinking maybe the time between the bond market crisis and COVID. So what was that, maybe an 8-year period or something? I forget exactly the numbers. Yeah, so you could get away with not having a time component then. But on the other hand, if we're looking over a 40-year time period, maybe put in a t or a t squared in there to take into account changes that might be due solely to the fact that something's happening in the industry, or and before I show you anything, I want to let you know that no matter how many items we put in a model, there's noise. There's going to be COVID that can't be accounted for in most models, right? There's going to be the bond market crisis. There's going to be the Braves losing the World Series. All these things can cause an issue, and they're not things that you can take into account. So anytime we can eliminate noise, that's great. And that's why, at least in class, I'm not necessarily disappointed if you can explain 20, 30, 40% of process variation. That's pretty good sometimes. So in terms of data processing, like I said, we had a lot of factors that weren't really independent. Some of the sectors had a lot of companies, 37, 31. The data is basically from 40 years, but we received it. Actually, in some sense, I've never seen cleaner data or more well laid out data in the first iteration. When we get a hold of it, it looked really good. I remember the previous year, maybe 2 years ago, we received data from a certain airline close to us, which I won't say, and I was getting numbers like planes taking off before they arrived because people weren't converting time zones properly. Lots of things like that. And this is coming from. I hope I'm not insulting anybody here. I mean, I love that airline; it's great, but this is coming from data analytics people, and I was a little surprised by that. But whatever. And so we love the airline. Okay, so the good news here is that the data was laid out pretty well. And even if Joseph or Gamza or I encountered a problem with the data, we call Regina up and we say, oh, yeah, there's a zero in this field because they didn't report data. And we would either delete that, because sometimes you have to do it, or we would impute proper value. What does impute mean? It means we would make a reasonable guess, maybe interpolate between adjacent points, something not stupid. Okay, this is not a statistics class, but I do want to talk about data gone bad, horrible data. And sometimes a model, you'll have to differentiate between what are known as outlier points and influential points in a data set. If you've got millions of pieces of data, or hundreds of thousands of pieces of data, you're going to get some crazy guys. And say, for instance, an outlier can be one of your input values or one of your outputs that's just way off the chart. Let's say plus or minus 2 standard deviations or 3 standard deviations. The software that we use automatically detects outliers and it warns you. All the good software does. We use R usually, which has nothing to do with R squared. R is the name of the software. It's the pirate software. So outliers may indicate that that's just a very unlucky point. Maybe Einstein walked in the room or something. I guess that's lucky. Or it could be just a bad piece of data. But what the software will do is it'll identify an outlier as something you should take a look at. You may decide to keep it in because it truly represents the data, or you may decide to kill it off, get rid of it. An influential point turns out to be a point that if you removed it, it would really change your regression equation a lot. Typically, it's an outlier, but it would really change your regression. Think of it as a lever almost. If it's right on the regression line, it's not going to affect things much. But if it's a little bit off the regression line, if you take it out, it could change the line a lot. And so there's some little pieces of trivia here. A point can be an outlier without being influential. That's for another day. Okay, so for the second or third time, here's our initial work that we presented few months ago. We start out with chemical, food, and pharmaceutical industries, 40 years of data. And like I said, we chopped the data up into every imaginable way. We looked at all 40 years. We looked at 10-year increments. We looked at interesting increments. And we conducted a correlation analysis to identify clusters, and then settled on 5 independent clusters, at the time at least. And we picked a representative factor from each cluster. So you could have one cluster might have 20 items in it. And we said, based on conversations primarily with Laura and Matt, we chose one representative, meaningful item from each cluster and put that in our model. Now, those things that we chose from the clusters eventually morphed into the inputs that we use for our more recent models. And so we performed the regression analysis using up to these 5 factors, and we modeled 3 output quantities in the beginning. I think it's useful to talk about those for a second, and then we settled down, of course, on market cap per employee. Okay, so we decided to use market cap per employee, but there's also this thing called fundamental score, which Laura alluded to. And what that is, that's a bunch of zeros and ones that each company is assigned based on how they perform according to certain characteristics. So did they make a profit, or the things that I don't remember? There's 10 of them. They get a 0 if they fail. They get a 1 if they pass that criterion. You add the numbers up, you get your score. Okay, so it turns out that the fundamental score was not useful in helping us in any definition of the word value. So we dropped it. Laura can explain more if you're interested in that. But it turns out, surprisingly, even though it's called fundamental score, didn't tell us much. Not so fundamental. Do you want to elucidate, or did I misstate or anything? I'm perfectly capable of doing that. Laura's making an explanation now for people online.
All of the manufacturing retail companies are followed by investors, and basically they look at their reporting and they give them ratings based upon factors, and it's called the fundamental score. So when we started this, I was like, wow, this would be cool, right? Could we validate the fundamental score based upon supply chain factors? And we quickly found out it was not effective. So what we're measuring there doesn't really align with supply chain, and there's more work to be done. So anybody got any insight about the fundamental score other than that?
I can tell you that private investors don't have.
Okay, okay, all right.
It sounds like some kind of.
What do private investors look at?
They look at, number one, they look at revenue growth.
Number one, revenue growth. Okay, one, they look at revenue growth, two, operating margin, and three, gross margin. Now, we threw out gross margin because of issues of collinearity with operating margin. So
They're core.
Yeah.
Absolutely.
Yeah.
Yeah, that's great. Yeah, that's absolutely right. Those measures a little bit correlate with each other. Yeah, so cost of goods sold is an issue as well. I agree with that.
So there's a dialogue in the room about COGS, which is cost of goods sold, and Rich is talking about some noise and how people will actually determine it. And then cash to cash was brought up. And your question is, now we did not look at cash to cash because it's a compound metric. Cash to cash is driven by receivables plus inventory minus payables. And what's happened is we've been playing a shell game in the industry where we elongate payables, which artificially makes cash to cash look better. So I wanted to avoid compound metrics. So I did not really look at cash to cash for that reason. And, payables did have some correlation, but I really steered us out of payables where I had other alternatives just because, there's only so much that you can extend payables, right? I mean, it's sort of like writing checks that you can't cash. And so I wanted it to be something that was actionable and directionally positive for collaboration in the industry. Anybody else got a question here?
Yeah, I should also point out that, working with Kinaxis was really helpful because they, Matt and others drove a lot of the discussion. It was very, very useful to have them in the room. And by the way, if you don't like this dependent variable, pick cap per employee, no problem, give us another one. The analysis can be done, sort of quickly these days. So I'm gonna, this picture is like a joke picture. In the chemical sector, if you can look really, really hard, I'll try to magnify that. Here are 114 potential inputs. It turns out if something is light, it means that there's not a lot of correlation there. And you can, if you look really carefully, can you kind of make out sectors, sort of, or not sector, little clusters? You have to have a good imagination, but this is a joke in the sense that no human is able to see, all the rows and columns here. But I guess if you look really, really carefully, there's actually a number for each of this, whatever it is, 114 by 114 matrix. And it's color coded to denote strength of correlation, either positive or negative. And you can see, I guess the point here is that chemical and food are different. Although looking at some of the foods, there's a lot of chemicals in them, but they are different sectors and they have different useful inputs, and the inputs are correlated in different ways. And so, so that's why we would pick these different clusters for each of the sectors. Now, that being said, we did all this work, and after we made these models, which I'm about to show you, we noticed some similarities among the models, and then it allowed Laura and the team to evolve into sort of a second tier of easy models using sort of the same input factors, but we'll get to that. Now, I'm going to keep the watch open here because, okay, I don't want this to turn into a stats class, but I do want to show you that we were attempting to be as rigorous as possible in the analysis because there's just so much data. I'll go through this very, very, very quickly, just to show you that we kind of tried stuff. Well, these slides are going to be available if people want to see them. They can look at them afterwards. Again, I'll do this very quickly, just to give you an idea of the things that we were looking at. Then we'll finally show some models and see how they did. We conducted that correlation matrix. You saw a little bit of that in the last correlation matrix study. We could come up with quote unquote independent sectors, clusters among the 114 factors. We identified 5 of them. We ran certain types of regression. This is a forward stepwise regression to build up a model. How many terms do we need in the model? We start out with 1. We see how the regression does. We then go to 2 terms in the model, see if it improves. That's called forward stepwise regression. Then we removed outliers. If we didn't like some aspects of the model, we used something called Cook's distance. I don't know if people have heard of that. That's a very simple, trivial formula almost to get rid of outliers. And we remove them to mitigate against skewness in the data. We determine R-squared values for each model. R-squared, again, in plain English, it's the percent of variation of the system that's explained by the model. Does that make sense? So if you have a really simple model, it's not going to tell you much. R-squared will be near 0. If you have a fantastic model that just fits everything perfectly, which sometimes is not good, you can do overfitting, and it makes you more confident than you should be. But let's say everything's working fine. You have an R-squared of 0.9. That's fantastic. That's telling you that the model is explaining almost all the variation in the system. We analyze the residuals. Residuals is a fancy word for the errors that you observe. And an error is what you saw from Y charts versus what your model predicted for that data point. It's always going to be a little bit different, because you make a model, and then when you run the model, it's going to say, oh, if I had run it under the same conditions as I saw that observation, it's going to make a prediction. It's not going to be quite right, though, because I'm now using the model. And so we analyze the errors between our model and what we saw at the beginning. Those errors should be approximately normal, and you do what's called a residual analysis to assess that. And in fact, that's what this is talking about. Then this is what drives everybody crazy. Remember how I said I could lie with statistics? I could figure out ways to get you a great R-squared, and then they'll pay me a lot of money for my wonderful consulting, and it's a terrible model. Let's see, my R-squared could be very high, yet if I look at the individual terms of the model, none of them is statistically significant. So it's kind of like saying each individual term is telling me nothing, but the model as a whole is telling me a lot of stuff. That can't possibly work. Would we agree with that? And it's because the main cause of this phenomenon is that the terms are artificially correlated, or they're truly correlated, and they're artificially increasing R-squared while telling you nothing. Okay, that's kind of like a lot of teachers. Luckily this is not on tape. Oh, it is. Yeah, I apologize, guys. Yeah, I'm old. If they fire me, it doesn't matter. The way you test for this crazy correlation is using something called the variance inflation factor test, VIF, variance inflation factor, and it's testing for this phenomenon. The phenomenon is called multicollinearity. That's named after a certain highly mathematical geometric interpretation of what's going on. But what it's doing, that you can calculate a VIF factor for each input in your model. So if let's say I'm looking at my weight, the inputs for my weight might be my height, my age, my blood pressure, and I could use those 3 things to estimate my weight. But what if I use my height in inches and my height in centimeters, or whatever these European people use? Those 2 things are obviously very correlated, right? And that would cause a problem. I would get a variance inflation factor, which is very high. This is the threshold. Usually if you get a variance inflation factor of 10, you're worried. And what do? You get rid of one of the terms, get rid of one of those terms that are causing the issue. Yeah, that's usually what you do. Okay, and it turns out, can you have some correlation and no VIF problem? Yes, it is possible for 2 things to be somewhat correlated, maybe not really, really, really correlated, but there not be a VIF issue. So you keep it in the model. Okay. Then we use, have you heard of a QQ plot? It's a way to quickly tell if these residuals, which we care about, are normal. So that's saying, are the errors in our estimates normal? And that's a fancy way of saying, is our model behaving itself? So you'll see some QQ plots in a little while. And then you can look at histograms to see if the residuals are normal. And then I won't do these right now, but if you don't like your data, if something's going wrong with the data, there are ways that you can do some mathematical transformations to the data to make it behave better. Joseph, by the time he was done cranking all these things through, he had the ability to hit a button, go and have a coffee, and it would go through several hundred, several thousand different potential models to find the best one. It's sort of his version of machine learning. Get rid of the redundant response variables. For instance, inventory turns, they were redundant. They're highly correlated, and get rid of them. Okay, and then, so here's sort of a full flow chart of what I just talked about. I won't, yeah, okay, yeah. So the suggestion is, why can't we come up with a linear combination of the highly correlated variables? We could do a factor analysis or principal components analysis. That was a constraint that we were not allowed to consider because we have the overarching two things that we have to balance out. Remember, we're having all these fights with Laura. We have to make the model rigorous, but it has to be simple and usable. Believe me, people in industry don't want to be dealing with eigenvalues. However, the deal I have with Laura is that when we're done with this, we are free to do whatever we want and then have a second conversation with it, right? I mean, that's completely fair. But we want to have somebody use these things, so we're going to keep it easy for now. By the way, the suggestion is fantastic. Correlation is not necessarily a bad thing if you know it's there. If you know it's there, you can do something about it. For instance, if I want to compare two different medicines for the same treatment, I don't want to compare the medicines with two completely different populations because that introduces a lot of noise. If I want to compare, let's see, how does it take longer to parallel park a Honda or a Cadillac? Do I want to do that experiment with two completely different sets of people? No. I want to do the experiment with the same person parking both cars because those times will be correlated, right? If I'm a terrible driver, it's going to take me a long time to park both of them. If I'm a fantastic driver, maybe it'll take me a very short time to park both of them. But if I'm a fantastic parallel parker, it'll take me a very short time to park both. So those times are correlated. That's a good thing, as long as I know that it's there. But here, we're doing these models, who knows? So I would say principal component analysis, factor analysis, excellent suggestion. We'll do that later on. Oh, that's what VIF is. VIF is measuring that. Yeah. Yeah, VIF is measuring that. Yeah. Yeah, spurious correlate. Yeah, I think I know the term. Yeah. Mm-hmm. Oh, yeah. The question was, is there a specific test to detect spurious correlation that might be explicitly causing a high R squared but non-significant independent factors? And that's what VIF does. But you might be right. There might be this thing called spurious correlation yeah. Oh, well, yeah, what it does in 10 seconds. No, VIF pretty much reruns the regression and it takes into account the new Y values that it would predict. Yeah, so they're in there someplace. Yeah, it reruns it for every single, it's tedious. It reruns it for each independent variable. And that's why you can't do it by hand. You push the button in R. Yeah, but that's okay. If you know that they're correlated, you can use one of these other techniques to deal with it. Maybe in these simple models, you just use one of them. Yeah, Katja? No, we only looked at, yeah. So Katja is asking, did we look at different methodological models like Poisson regression, logistic regression, things like we didn't because of the nature of the problem. We were looking at these continuous outputs. So Poisson would be good for counting, and logistic regression would be good for numbers between 0 and 1. But yeah, but those are all on the table depending on what problem you want to answer. Okay, yeah, great questions. Okay, I'm going to show again. I'm keeping track of time. I'm the only person standing between you and a break. So you got lunch. That's like kind of critical, isn't it? Yeah. So here are some of my favorite prime numbers that I'll recite. So I'll give a sort of a synopsis of some of the results. These are from the initial work, and I'll talk about some of the other things we did when we settled on an overarching model. This is a typical example coming from one of the three sectors that we did right at the beginning, 4 or 5 months ago. And again, this is market cap per employee. And here are the inputs. We use 5 inputs here: profit margin, annual net income, et cetera, and time. These betas, so-called estimated coefficients of the model. I'll show you precisely what I mean by that in the line below. And I'll show you what some of the output characteristics look like. This line is incorrect. Not sure what that's doing there, but this is this is predicted value versus observed value. And you can see that they're definitely highly correlated with each other. If you have a low predicted value of market cap versus what you actually saw from the inputted data, you would expect them, in a perfect world, they'd be exactly the same. They'd be right on the line. If you had a high predicted value, you'd have a high observed value. But the fact that they're at least kind of correlated it's a really good thing. And anytime the number they're not exactly the same, the straight line should probably be right in the middle here. That's an error in some sense. So here's what the model is. So this predicted market cap per employee is this equation. And here are the betas. And X1, you input the profit margin, you input the net income, et cetera, et cetera. Even here, you input time, and time must be, it's probably shifted over probably the year starting in 1980. I'm not exactly sure. The key performance statistics are this R squared, which indicates that it's this model is doing a pretty good job predicting the Y values, predicted market cap per employee. This F statistic here on the bottom means that this is not a statistical anomaly. I mean, it's telling you something, a statistically significant output. It's telling you something. That means the regression is not just giving you nonsense. And this thing, this Jacques Barra, that's indicating that the data it's a stone's throw away from having normal residuals, which is a good thing. So you can see this is, a really simple model. We didn't do any tricks to it. The reason I'm showing this is because George Runger's model, and again, this is a model from many, many years ago, he was getting R squareds 0.1, 0.2, and he was getting crazy looking plots because the data were correlated in certain ways. I mean, actually, they're very pretty, some of the plots, but they had nothing, they weren't these nice, kind of fields of points. So that was pretty good. And Joseph did this for each sector. This is price to book. Can somebody tell me what's going on here? Compare these two pictures, that one and that one. Which one has more noise? Price to book. Yeah, so that means it doesn't necessarily mean that price to book is the world's awfulest, most terrible measure, but it is certainly saying that it's definitely harder to predict. There's just more noise there. Surprisingly, which is amazing to me, residuals are behaving a little bit better, but that's fine. But the R squared is half of the model market cap. So this is just to show an example here. By the way, you may also see these betas fluctuating wildly. 5,000, 0.003. Does that mean that the 5,000 is, 5 million times better than the 0.003? No. It means that the X's are scaled differently. So remember, these betas are multiplying these X's, and the X's are just different units. And so they're scaling things differently. So don't get upset if you see wildly changed numbers. So because we knew that people would be getting upset about seeing wildly different betas in the final work, which I will show you in a little while, we tended to scale the betas and the X's in such a way that all the numbers were more or less in the same ballpark, the same orders of magnitude. So it wouldn't look like they were, crazy different units. And again, this is to make things easy to use. It turns out you can rescale the X's and the betas and not change the regression at all. You get the same results. You're just changing the units. That's perfectly okay. Okay, here's the food sector. Yeah, this is doing pretty well. Same thing. And notice that we have a slightly different set of independent variables here. And this is for the old stuff from a few months ago, but it's a slightly different set. You don't need to look at them specifically necessarily, but you can just see that they're a little bit different. Okay, pharmaceutical sector. The nice thing is lots of data, pretty well behaved. And it's owing to the fact that Regina obviously took a lot of time preparing the data. And again, having worked on lots and lots and lots of practical problems, over my long lifespan, it's nice to have data that's given to you that's in pretty good shape to begin with. Now, we did do stuff with it, you'll see in a few minutes, but we had a huge running start because it was given to us in a nice form. Okay, so this is great. I'm totally surprised that all the models are kind of working. Having seen George's results, I thought we were going to have a lot of trouble. I remember we had a former student was doing a project for KPMG, and she came by, Gams and I helped her with the project 3-4 years ago, and she ended up getting R-squareds of about 0.15 for her models. This is KPMG. What do they charge? Several $1 million a day. The client was okay with that because it's told some story. It wasn't a completely statistically insignificant story. So the fact that we can get a surprisingly high R-squared of 0.75, I'm happy with that. Now, if I was using stock market prices to predict the value of an Asian call option, I would want an R-squared of 0.999 before I made a decision on something. But that data is perfectly minute-to-minute clean data, and this is sort of a different animal here. There's a lot of noise going on. Okay, so then we also put sectors together. These were the 10 inputs that appeared in these 3 sectors. We were able to make, say, a gigantic model based on all the data from those 3 sectors. So this is just to show I could do lots of stuff. That's that's sort of the synthesis of this analysis. One other thing that Joseph did, which I'm not going to show you here, is that we also, this is automated, we looked at a number of data transformations, higher order models, things like if I'm interested in estimating my weight, I could use my height. I could also enter in the term height squared. Blood pressure, I could enter in the term height times blood pressure, things like that. Those are called higher order mixed models. I'm allowed to use those. And so he looked at a bunch of these things too. So we kind of looked at everything. Okay, and these are various correlation matrices of the selected terms from each model. So these are just kind of bonus things. This is a QQ plot. I wanted to show you one of these. A QQ plot, and this corresponds to the chemical sector, whatever the model was. It had an R-squared of 0.498, whatever the model was. Looks like it was profit margin, total operating expense. So these are the inputs right here. I wanted to show you this slide because this is in order to show that a model is working, it has to satisfy the assumptions that linear regression is based on. One of the assumptions is that these residuals, these error terms that you have, are normal. It can be shown if the observations, I'm not going to really define what I mean by observations here, if they fall on this red line, then that's showing that the residuals are normal. Okay, if they don't fall on this red line, that means I can tell you that these observations, whatever the distribution is, it's got a really fat tail. Means that you know how the normal distribution comes down, nice beautiful bell curve. The bell curve comes down to 0 very quickly. That's what we mean by plus or minus 2 standard deviations. If it's got a fat tail, that means that every once in a while you get a crazy observation way out here. And do we like crazy observations? No, else I wouldn't call them crazy. So this is something that messes up your model. And I would say, not so great. This is not the worst model I've ever seen. George's models, the blue line was like coming up here. It was like all over the place, absolutely crazy. I would say there may be some outliers in this model. That's what this is telling me. Gams, is that what's telling you? Yeah, some outliers. Or we could apply a transformation and maybe they go away. But anyway, that's a standard statistical tool, which I wanted to show you. Now, let's get serious. So I've kind of given background. We now have the ability over the last couple months, as I mentioned, Joseph cranked out every single sector, and we actually underwent another data cleansing because now there were some zeros and other small issues that snuck in. Again, Regina was very patient and very helpful. And I'd say you're satisfied with the data now? Everybody's happy? Or impute. Yeah. So yeah, Joseph is explaining that some of the companies, for whatever reason, didn't report certain data. And sometimes we get rid of that line, or sometimes we impute the missing data point. Okay, so what I'll do now, I'm right on schedule. I'll give a couple easy examples and just keep all that statistic stuff that I talked about in the back of your minds. And this is automotive parts aftermarket sector. We're blanking out the betas because I don't want you wasting your time on those. These are confidence intervals for the I guess they can reverse engineers what the betas are. The only thing we really want you to see is this wonderful, nice big fat R squared. This is after a second major round of data cleansing. Let's see. I see a very small JB number for normality. I'm seeing good stuff here. And this is now, remember, we want to keep the model simple. And Laura is saying having 15 inputs, 10 inputs, not simple. Let's sacrifice a little R squared for tremendous simplicity. So now we have a model with 4 inputs. We did not include time. T doesn't mean time here. It means something else. We could include time. Joseph, was this for a 10-year period? Okay, I suppose we could have included time as well, but we got this R squared 0.64. So we got rid of most of the factors and we sacrificed 10% on the R squared. Okay, I'm willing to make that trade-off, I guess, now with my newfound knowledge. And look at that. That is a nice looking QQ plot. And for those of us who care about adhering to the assumptions of regression theory, we're pretty happy about that. Who could not possibly be happy about that, right? And so another thing we're happy about, see these numbers here? VIF 1.4, 1.28. What does that mean in English? It means that none of the inputs are remotely correlated with each other. They might be correlated, but they have no effect on multicollinearity. There might be a little bit of correlation, but whatever's going on here, this is a valid statistical model. And as Laura mentioned a little while ago, we haven't done a formal validation testing yet, but I'm 100% confident that this model is doing what it's supposed to. And it's giving pretty good R squared, and it's simple, and it's adhering to the assumptions. That's nice. This is containers and packaging. Look, big fat model, nice little model, even smaller model. And now the R squared is 0.575. Yeah, we lost again about 0.1 on it. Okay, that's fine. And this model, even though you got a few little outliers here, not so bad. And what was JB on this? 7 point. Yeah, this is fine, more or less normal. So it's work. Yeah, Laura's mentioning that this data was a little bit polluted by COVID results, but it's still working okay. So that's great. And then I'd like everybody to memorize these numbers real quick. This is a summary slide of the regression models for each of these industries, sectors. And you can see, don't worry about this, obviously, market cap per employee annual with the same inputs, operating margin, revenue per employee. So generally speaking, these are the more or less the same inputs, which indicate kind of a surprising robustness of the inputs to the market cap. And here the R squareds, all pretty decent, nothing too bad. And we'll give you the slide so you can look. I'm glad to see that Joseph included 97,000 significant digits here. It's a joke, little statistics joke. And then I'm going to spend 2 minutes talking about, this is the old bad fundamental score.
One that's the outlier. But other than that, the industries are very small. The models are pretty self-explanatory. And even though you do a lot of work around refinements, the metrics that matter are operating margin, return on capital employed, ROCE, which is slightly better than ROIC.
Yeah, which we have here.
Return on invested capital. And inventory turns and revenue per employee.
Right.
So it's like different variants of those 4 metrics across the industry. However, how well do we measure those in the industry? Mary? We don't, right?
Oh.
Anybody measure those in supply chain decision making? We don't. Right, and the functional areas are really looking at cost, right? And I think, this afternoon, we're going to talk about those 4 metrics and what do we do differently to move those forward? What is the role of the supply chain to move those metrics forward? Yeah, but the industries are pretty easy to model.
Yep.
Pretty good models, with the exception of automotive.
So I'll just have a couple more slides then, because I see some lunch action going on here. This fundamental score that we've talked about a couple times, we really want to do our own fundamental score, and you guys will be very helpful in determining the components of such a score. But I guess it's sort of simple-minded. What people currently do with this particular fundamental score metric is that they test to see, is EPS growth positive? Is revenue growth positive? Every time one of these succeeds, you get a 1. If it doesn't succeed, you get a 0. You add these up, that's your score. And I think we can do more meaningful score than that, but it's going to require some discussion, I think. Okay, and so maybe we can talk about this a little bit later. Fundamental score for the supply chain, I think we should certainly include the metrics that were included in our models that we just showed you. Okay, so next steps, this is my last slide. We're doing a comprehensive examination. We're going to try even for slightly better models. There wasn't really a time deadline on us. Look into the reasons why each sector is performing as it does. We're currently validating the model on, typically what people do, you make your model and then you validate it on upcoming data that you hadn't seen yet. And that's what we're doing with 2023 data, although we've encountered some conversion issues, and that'll be coming up pretty soon. I think once that's done, then then I can, aside from saying how the QQ plots look good and all the assumptions are satisfied, then we'll be totally happy about it. So, okay, I think that might be a good place to stop. Does anybody have any questions? Yeah, I'm sorry I went so fast. I mean, you kind of get stream of consciousness from me, but you're asking, yeah. So the question is, within a particular sector, are any companies identified as outliers? Huh. Yeah. So clearly what we would do is we would look at the different X values that it gives us and the different outputs, the Y values. And I guess if a company is, more than say 3 standard deviations away in any of those measures, we'll flag it. And Joseph, you're doing that right now? Yeah, Joseph is explaining that we flag all the outlier and influential points and look at them, possibly deal with them. Does that sort of answer your question? So we haven't gotten to that point, but it's close. So you're saying if we replace one of our inputs with a different, say, reasonably similar one? Yeah. I'm not sure what would happen. It's probably, if it's similar, the R squared will behave in a similar way. Yeah, not sure what would happen necessarily, although Joseph, yeah, so Joseph is answering in line with me. If you replace something by a more or less, order of magnitude similar input, it's not going to affect R squared by much. For well, I don't think we have a high-tech sector identified. Yeah, it's B2B tech, right? Yeah, so telecom and B2B tech. Yeah, semiconductors too, yeah. Laura's explaining the difference between these and semiconductors. Yeah, how's time model? Okay, so I think what we've done is that at the beginning point of the data collection, let's say it's a 1980 to 2020 regression model. T starts out at 0 and it goes to 40. And so it's just linear time. The effective time changes from sector to sector. And sometimes, I think sometimes it's not even significant, but in some of the sectors, it's definitely significant and helps you increase R squared. Yeah. And Gams is pointing out that it's almost always significant. Oh, you start at 1, not 0. Okay, yeah. Question?
Did that answer your question? We good? Okay, yeah. Question?
This inputs the other model, thinking about,
Okay.
Talk about this after. And putting it in practice, there are going to be functional leaders making decisions with this information.
Sure.
And there's no functional leader of operating part, per se.
Well, that's what we're gonna do after lunch. So
Okay.
next we're gonna grab a sandwich, and then Peter and I are gonna talk about the score metrics versus what we learned here. And then we're going to put you into tables and discussion groups, and we're gonna ask, how does this change behavior? What would we do differently to improve operating margin or to drive inventory turns? Would we not improving inventory turns or revenue per employee? So that's what we're going to do after lunch. And Peter's going to put the people online into groups. Okay. And we're going to capture those outputs. That's where we're headed. Right. Other questions? Because you're right. What this is telling us is not what we're either modeling as in decision support or driving at a behavior level in terms of process design.
That there's a discussion going on in terms of implementation necessities.
Okay, other questions? Yes.
So the intention point for deriving intention point, have you like removed the outlier data from there and check the derivability point? Because either you, I mean, the way I look at the output of it is like you can either you can if you end up play around with the outlier data, you can see the variance in the results now.
Yeah.
Predictions.
Mm-hmm.
So my question is like when you derive the intention point, have you removed the outlier data from there? On the rest of the data you actually derive the intention point?
Yes, we looked at the explain outlier.
Yeah, there's a question going on now about removing extreme outliers and influential points.
And then after that, we will.
Sounds like a good lunch conversation.
There's a big fight going on. It's getting physical.
No, it's not funny. But yeah, it's a good lunch conversation. Other questions here? Okay, we're going to, it's 12:03. I'd like you to grab lunch, bathroom, and we're gonna start again at 12:30, okay? So if we could do that, lunch is here. I'll get the wrap off the lunch.